Okay, Assalamualaikum warahmatullahi wabarakatuh and a very good day. So basically this is a continuity from your basic material science lecture that you have learned this week. Okay, let's start.
Okay, question number 1. This is a graph of force versus distance between atoms. So the question would like us to find an equilibrium position of the atoms, between the atoms. Okay, so we understand that the atoms experience equilibrium position when there is no net force acted to them. So therefore, from the graph, we could actually refer to the force, which is fall on y-axis, and the value of 0, or net force is equivalent to 0, will actually lead to the point Q. So our answer should be B. Question number 2. The graph is actually shows the variations of force between two atoms with their separations. Okay, so the question is asking us to find which of those statements is true. So we look at one by one. From option A, it is stated that from P to Q, the resultant force is attractive. So where is P to Q? P to Q, it's somewhere here. So we can say that it is actually fall under positive repulsive force. So it is actually not an attractive force. So A is wrong. Okay, we look at point B. From Q to R, the attractive force decreases. So what about from Q to R? From Q to R, the value of force, it started off with the value of 0, even though it is going downward, but the value is actually increasing in negative value. So this statement also wrong. Looking at statement C, and R, the attractive force is maximum. So attractive force is maximum, set at R. Okay, so it does make sense, but why don't we take a look at option D? From R to S, the resultant force is repulsive. So from R to S, the resultant force is repulsive. We know that on the negative side of this graph of force versus separations of atoms graph, the negative side is actually showing negative attractive force. Therefore, the statement of D also wrong. So the best option would be C. Question number 3. What is question number 3 stated here? We have graph A and graph B shows the interatomic force F and potential energy U plotted against separation R between pair of atoms. The graph have different scales on the x-axis. Which point is correct to represent the equilibrium separations of atoms? So we look at graph A. It is force versus separations of atoms. So the question would like us to find equilibrium separation between atoms. We know that already from our previous question. Equilibrium state of atoms when the atom experiencing no resultant force. Therefore, F is equivalent to 0, which position is showing Y value. That is for A. And what about B? B is potential energy versus separations of atoms. So when it is in equilibrium states, when the atoms are in equilibrium states, we know that they are not moving. They don't have any thermal energy or kinetic energy related to them. So therefore, their potential energy is very minimum. So very minimum, it's somewhere here. Okay, somewhere here. So it is at point Q. Question 4. Again, the graph of potential energy between two molecules with separation R. At which point on the graph does a change from the solid state to liquid state take place? So a state is changing from solid to liquid. So we know that when the state of matter is changing, meaning from solid to liquid state, the force of attraction is reaching the maximum point. So beyond that value, the value of force is they cannot withstand the attractive force anymore. They will break the bond between the molecules. So where is it? Where is it? So this is actually the point when the bond starts to break. So this is considered the maximum attractive force that the molecules could withstand. And beyond that, they will break. So meaning that the state will change from solid to liquid. So this as is inflection point. So the answer for this is D. Graph below shows the variations of potential energy with separation distance r from two atoms. So the question is asking us to check on the D minimum in the curve, what is actually corresponds to. So the D minimum of this curve is basically related to our previous question, stating that it is the minimum energy, a minimum potential energy where it reached the stability of atoms or equilibrium position. So basically the answer is stability. B, the bond energy is stable between the two atoms. Question 6, if the atoms are pulled to a very large separation distance, which is R equivalent to infinity, the potential energy approaches which value? We know that when at infinity, the atoms will no longer experiencing attractive force. So attractive force is equivalent to 0, meaning that potential energy also equivalent to 0. Moving on to question number 7. A steel wire with cross-sectional area of 2 millimeters squared is subjected to a force of 200 Newton. Calculate the tensile stress in the wire and give your answer in megapascal unit. So what we have over here, cross-sectional area of 2 millimeters squared and force is in 200 Newton, and the final answer is required to leave it in megapascal. You really have to be careful over here. You need to check on the conversion unit. Okay, so area is in 2 millimeters squared. So what you need to do is to convert this first. So 2 millimeters squared, we know that 1 millimeter is equivalent to how many meters? 1 times 10 to the power of negative 3 meter. Am I right? So 2 millimeters squared would be equivalent to, so 2 millimeters squared, 2 times 10 to the power of negative 3 times 10 to the power of negative 3 meters squared would be equivalent to 2 times 10 to the power of negative 6 meters squared. Okay, so this would be our new area into meters squared. Now, tensile stress. What is tensile stress? Stress is equivalent to force per unit area. So force is 200 Newton over, is still in SI unit, so doesn't matter for that. Over our area is 2 times 10 to the power of negative 6 meters squared. So Newton and meters squared. So 200 divided by 2, it's 100. And the negative we bring to the top will become positive. Newton per meter squared. This is equivalent to Pascal, and this is equivalent to mega. So therefore, our final answer would be 100 megapascal. Okay, let's continue with our exercise 8. So the question is asking us to find the strain, given that elastic band is 5 centimeter long, stretches by 2 millimeter. Again, we have to convert. We do have to do conversion. So 5 centimeter long and 2 millimeter stretches. So 1 millimeter, we know that is equivalent to 1 times 10 to the power of negative 3 meter. And 1 centimeter is equivalent to 1 times 10 to the power of negative 2 meter. So once you do your conversion, it's easier for you to substitute into the equation. So what is the equation of strain? Strain is equivalent to extension divided by the original length or the initial length. So what happened here, delta x is the stretches one, the extension, which is in 2 millimeter. So 2 millimeter is 2 times 10 to the power of negative 3 meter is in SI unit. And the initial length, which is in 5 centimeter. So 5 times 10 to the power of negative 2 meter. And we know that meter and meter could be cancelled out, and which is proof that the strain doesn't have any unit, or we call it dimensionless. It is only represent with value or number. So when we substitute with the values and cancelling the unit, we will have the answer for this one is 0.04. That is question number 8. What is the question number 9, Luke? Want us to find? It is asking us to find the Young modulus where the values are given, most of those not in SI unit. So again, we have to do conversion. A steel wire of diameter of 0.4 millimeter. What else do we have? Initial length of 2 meter. Is hung vertically from a fixed support when the Newton or the force is 80 and the wire extends by 6.4 millimeter. So what are the values given? Diameter. So let's take a look at diameter over here. It is at 0.40 millimeter. So when we convert, it is becoming 0.4 times 10 to the power of negative 3 meter. The initial length is 2 meter, okay. In SI unit already. Force is in 80 Newton, also in SI unit. But the extension is in millimeter, 6.4 millimeter. So when we convert, it will become 6.4 times 10 to the power of negative 3 meter. So we have the value over here. So let's try to calculate the Young modulus. What is Young modulus? Young modulus is the stiffness of the material, right? So the stiffness of the material here is wire. So Young modulus is stress over strain. So if we substitute stress, stress is force over area over strain is extension over initial length. So when we rearrange that, it will become force times the original length over A times delta x. We have all the value, but we don't have the value of area. So steel wire, what is the area of cross-sectional of the area of steel wire? We know that wire, it looks like this. So cross-sectional is actually a circle. So cross-sectional area of a steel wire, A is equivalent to pi d squared over 4. Substitute pi and diameter, which is 0.4 times 10 to the power of the negative 3. Don't forget the squared over 4. So compute to your calculator. You will have the area, which is somewhat 125.7 times 10 to the power of negative 9 meters squared. So we have the value of A, then we substitute the values into the equations of Young modulus. So force is 80 Newton times the initial length, which is 2 meters. And then we have our area, which is 125.7 times 10 to the power of -9, with our extension 6.4 times 10 to the power of -3. Solve with your calculators. The calculation will lead you to the correct answer of 2 times 10 to the power of 11 Pascal. That is exercise 9. Question 10, it's an extension versus force graph. Be careful now. The graph that we have learned in lecture is a force versus extension, but this is when you flip the graph to x and y, vice versa. So extension in centimeter, force is in Newton. So for force versus graph of x or extension, delta x. So graph like this, you will have the gradient exactly as the spring constant according to Hooke's law. So K is equivalent to F delta x. But now it's the other way around, where the extension is on the y-axis and the force is on the x-axis. So the gradient here will give you what? Will give you 1 over k. We really have to be very careful on the value. So to find the gradient, let's find the gradient first. What's the gradient? The gradient of the graph is extension versus over the force. So extension, be careful, is in centimeter, 15 times 10 to the power of -2 meter. Need to be an SI unit. And the force is 6 Newton. You will have the answer is in meter per Newton, which is somewhat around 25 times 10 to the power of -3 meter per Newton. So reciprocal of this, 1 over 25 times 10 to the power of -3, you will have the answer for K, which is equivalent to 40 Newton per meter. Leads to D. Next question. A wire is extended by a force. The graph shows how the extension of the wires with a force applied. Initially, a force W gives an extension D. The force is then increased to 2W. This increases the extension to 2D, D from 2D, 0 to D, and D to 2D. Which area of the graph represents the work done by the force when the force increases from W to 2W? Increases from W to W. So W to W, W to 2W would be this graph. And then this you've learned the graph of force versus x extension, force versus extension, where the gradient will give you the spring constant or the stiffness of the material, and the area under the graph will give you the energy or work done by the force. So now it's the other way around, where now the extension is on the y-axis. So when the extension is on the y-axis, whereas the force is on the x-axis, so extension is over here and the force is over here, where will be the work done or the area of work done? So it will need to be located somewhere here. Okay, but now the question is asking you to find work done by the force when it is increasing from W to 2W, W to 2W. So it must be from this area to this part. Okay, this area to this part. TMRS. Next question, question 11. What is the question 11 is about? Is about shear force applied to upper face on aluminum cube, measuring 15 centimeter on each side. So you need to calculate the displacement of the upper face relative to the opposite side given the shear modulus as stated on the question. You may pause this video to answer the question by yourself, or you can continue to check on the correct answer. Okay, we know that shear modulus, what is shear modulus? Shear modulus is equivalent to shear stress over shear strain. What is shear stress? Shear stress is force over area, and shear strain is, what is it? What is shear strain? Shear strain is the displacement. There's no extension and displacement over the height of the material. So in this case, the height of the cube. And if we rearrange this equation, we will have force times h over the area times the displacement of the material. Okay, so again, when we look at the values given, we have 15 centimeter, which is not in SI unit, where you need to convert it again later. So, and the force given in SI unit. So substitutions of that, we have shear modulus as 2.5. So shear modulus is equivalent to F times H over the area times delta X, where substitution of shear modulus is 2.5 times 10 to the power of 10, and force is 500 Newton. The height of it is in 15 centimeter. 15 times 10 to the power of negative 2 meter over the area. Okay, area it's 15 times 15. So 15 times 10 to the power of negative 2 times 10 to the power of negative 2. Again, for meter and meter. And we need to find the displacement. Okay, rearrange this equation, you will have the final answer for delta x. What is delta x? The displacement is 1.33 times 10 to the power of negative 7 meter. Question 12. What we have here, a solid sphere of volume 0.5 meter cube. It is initially surrounded by air. The air pressure is exerted on it is given 1 times 10 to the power of 5 Newton per meter squared. And it is being dropped to the ocean at about 2000 meter, where the pressure is then experienced as 2 times 10 to the power of 7 Newton per meter squared. Calculate the change in volume of the sphere given the bulk modulus. Okay, so we know that bulk modulus equation is bulk equivalent to change in pressure over a change in volume over the initial volume. Where when we rearrange this equation, we will have bulk modulus equivalent to change in pressure times initial volume over change in volume. And we have the negative side over here, the negative. So this negative, we know that it's about the decreasing of the volume. Okay, when we rearrange this equation again, we will need to find the change in volume where it will become negative delta P times V over the bulk modulus. Okay, so substitutions of this negative change in pressure, final pressure minus initial pressure would be 2 times 10 to the power of 7 minus the atmospheric pressure to the power of 5 Newton per meter squared, and the initial volume is 0.5 over the bulk modulus, which is 7.7 times 10 to the power of 9 Pascal. So compute with your calculator. You will have the final answer for change in volume is equivalent to the negative 1.3 times 10 to the power of negative 3 meter cube. So this negative shows that there's a decrement of the volume. Okay. So I hope that from the exercises over here, you will understand more on the basic parts of the material. If you do have any question or any inquiries, you may email me directly or you can email Miss Jannah. Assalamualaikum and have a good day.